The last presenter is Yuri Lawryshyn from the University of Toronto, and it's a joint work with Matt Davison from Western University, previously University of Western Ontario. And Yuri's going to talk about using boundary fitting and machine learning to value multi-stage real option investments.
What I'm going to talk about, I'm going to talk a little bit about just the introduction, the motivation behind this particular work. And then I'm going to get into a little bit of the theory. I'm going to talk about a Bermudan put option, an American put option, and then talk about a simple build abandon problem, which is a very simple real options scenario. And then I'll present the results. I'll present the results of the Bermudan put. I'll provide a few example applications, the American put, the simple build abandon, and then I'll talk about some of the more future work where we're looking at stage investment, and this is where Maria already talked about learn as you go, and then also how we can potentially put this into a machine learning, reinforcement learning environment. Because what we really want to do is make this as automatic as possible. And then just brief conclusions. So the overall objective is to develop a real options tool that can be readily used in the industry. Okay, we want a practical tool that can be used in the industry. And I'm going to talk specifically in the context of mining. Why mining? Because first of all, in the mining industry, we have the futures market, which provides us a natural real options hedge. So we know what the futures prices are expected to look like. So it really allows for a nice valuation in terms of whether a mine is going to be valuable or not. There's significant uncertainty. There's systematic and idiosyncratic, which likely increases the real option value. So systematic uncertainty, clearly the actual real options price. But idiosyncratic uncertainty, there could be a number of factors, but the one that I'm going to really talk about is how much ore is actually in that site. Right? That's an idiosyncratic uncertainty. There was this work done by Auger and Guzman where they reviewed 51 mining projects in Australia, and it was done looking backwards, so in hindsight. What they found in hindsight was that less than half of the investment decisions were made at the right time, meaning less than half of the mines were built at the right time, either too early or too late. 36 of the projects should have chosen an extraction capacity of 40% larger or smaller. They concluded that irrational decision-making exists within the industry due to lack of real options tools available for better analysis. So if we can provide better valuation tools, arguably we can help the industry to make better decisions going forward. In terms of mining, systematic risk, the commodity price, foreign exchange, potentially political factors, idiosyncratic risk, quality of the mineral, quantity of the mineral, ease of extraction, cost of extraction are some risks. Decision-making complexity, when to build, when to expand, how big to build, when to mothball, when to abandon. What about optimal rate of extraction? There's never been any work done here. The mines either are on or off. But should you perhaps reduce your rate of extraction if you're expecting higher prices in the future when you know that there's only so much ore in the ground? So there's quite a bit of literature to do valuations for mines. Both the Canadian and Australian governments have manuals on how to do mining valuation. And then in real options models, there's been quite a bit of work done. Many of the models are based on lattice methods, trees, binomial trees, and that. And there's some work done through Dixon Pindyke and Schwartz. More recently, some least squares Monte Carlo methods have been utilized as well in real options valuation. And then some work here done by Yuri, 92 academic papers. I found that most models focus on very specific situations, and most models consider only one or two real options. Right? So clearly there's opportunities for improving the models. Here, another set of authors reviewed the valuation of American options. So what is an American option? Basically, it's an option to buy a stock at a certain fixed price that you have already agreed to today. or sometime in the previous, at any time through until some time that the stock is no longer, the option is no longer available to you. So that's an American option. So an American option means at any time I can invest, or at any time I can stop and get out of the investment too. Bermudan is similar to the American. It's just that instead of on a continuous basis, it's on a discrete basis. So often in industry, managers aren't looking every day to see if they should stop their investment and do the investment. They might look on a quarterly basis. So arguably, Bermudan options are more like what happens in industry. The problem with American options, though, is that they are harder to evaluate. And I'm going to show you some examples here. And so there are a number of different ways to do this. One of the leading ways is least squares Monte Carlo, using dynamic programming, but this has a problem, and I'm going to show you what the problem is here. So you've already seen this slide, but I'm going to go through it in a little bit more detail. So we have this price process. So today the price is $10. Half a year from now, or half a period from now, or whatever, it can either go up to 10.7 or down to 9.3. 1 year from now, it can go to these 3 states, and so on. And clearly we can expand this. It doesn't have to be discrete as shown here. And then we have a cash flow process where if we're running the plant and the price is 10.7, then we're going to have a positive cash flow of 3.7. And if the price goes to 9.3, our cash flow is going to be 3.4. And the cash flow process continues as follows. Right? So that's just how it is. There's also an abandonment cost here. I'm not going to get into details, but somehow we came up with this cash flow period based on this price process and some other factors. So now the question is, when should we build, or should we build right now, or should we build sometime in the future? And we're also going to assume that if we decide to build today, it's going to take half a year to actually start achieving the cash flows, because it's going to take us half a year to build the plant. So if we build at year 0, what happens is we will generate these cash flows, and so there's going to be initial investment cost and so on. But ultimately, the valuation tells us that if we build at year 0, the valuation of this plant is going to be 0.6. Okay. On the other hand, if we wait half a year and the state goes up to this upper state, which would be this 10.7, and we build here, then we start gaining our cash flows, and the valuation comes down to 5. On the other hand, if we didn't build this year and we went into this state of 9.3, then the valuation tells us don't build. Right? Now, because this 5 is greater than 0.6, clearly what we really should do is not build today, because that's only going to give us an expected value of 0.6, but rather wait half a term. And if we wait half a term, if things go down, we do nothing, we walk away. And if things go up, then we're going to achieve an expected valuation of 5. It's much better. Now, on the other hand, if we build at year 1, so if we don't do anything here, but we build at year 1, what this is telling us was don't build in this state, don't build in this state, but do build in this state. And if you do build in this state at year 1, your expected value is going to be 3.1 at that point, which actually, I should say that your discounted value to time 0 is going to be 2.9 here and 1.0 here. So what you then do is you look at the highest number, and the highest number is 2.9. And what that tells you is this is the most likely scenario to go, but it also tells you, comparing this to building today, wait. Right? Wait at least a period. Now, clearly, if you wait a period, everything can change. And then you have new assumptions, you might want to rebuild your model. But this is what real options is all about. And so what we're saying here is there's value in waiting. Because if we build today, our expected value is 0.6, and if we wait, we could potentially achieve an expected value of 2.9, which actually could even be higher if things work out a certain way. Okay. Now, you realize that even for this very, very simple problem of just building and trying to figure out when to build, and we only have a few little states here, we have to build a model for each. We need a new lattice for each case. And this explodes when I want more accuracy. So let's say I'm going to use many more time steps. And I have many more valuations here. And if I want to go into some sort of continuous model, it's even more difficult. This happens with least squares Monte Carlo, it happens with everything. So we need to get around this issue. And the way to do this is through simulation and building a boundary. So here are some simulated paths of a price process. And what we can do is we can say take any one of these paths and we can fix a boundary here. And we don't know where that boundary should be. So we could start off with some initial guess. And we can start off with an initial guess of a straight line. Doesn't really matter. But if any one of these paths crosses this boundary, we then know we build. We can wait a half a year to build our plant. And then we can generate the cash flows from having that plant built. Okay, that's how it works. So what we then can do is once we've simulated 100,000 of these paths, because these are all potential paths. Every one of these things can happen. It's just like this. It's all the potential scenarios that could happen. And if we generate 100,000 of these paths and we optimize this boundary on maximizing the value today, expected value today, our algorithm will eventually pick the correct boundary here. All right? And so what I now have done is instead of using multi layers as I would have to have done in least squares Monte Carlo, I only have one layer of paths that I have to deal with. And I can build this exercise boundary, and it tells me when is the best time to build as a function of time and price. Now, in this model, I didn't even look at abandonment. But if I add abandonment, I need more layers. I need a layer for every time that I've built at a certain period and then abandon afterwards. So now this explodes. But I can do the same thing here by saying, okay, I'm going to start with one boundary here and one boundary here and optimize the parameters for these boundaries so that if my path crosses here, I build, and if it crosses this path, I abandon. And then I can optimize on my valuation based on how the parameters change for running this line and the parameters are changing that curve, and then I get my optimal solution. So now the question is, does this work theoretically? Does it match the theory? And that's what I'm going to talk about. So the overall objective is to develop a practical simulation-based real options methodology that can model realistic decision-making scenarios encountered in industry. But what we really want to do here is this idea of fitting the boundary, does it match theory? All right? And we'll look at it from a Bermudan option, an American option, and then some example applications. Okay, so Bermudan option, in this case, what I'm saying is I've got some time halfway through or some time tau, so there's capital T is the end of my option. I can no longer, my option is either I invest in the option at capital T or I don't invest, depending on what it's going to pay off. But I can also exercise the option early, right? So it's a Bermudan option, and I only have one time to exercise early, and that time is fixed. So basically, you can think of capital T as the termination of the option, and tau is that one Bermudan time that's fixed that's earlier. So for example, the contract could say T is 1 year and tau is 0.5. So when time comes out to 0.5, I can either exercise the option or not, depending on whether it's worth it or not. And at capital time T, I can exercise the option or not, depending on whether it's worth doing it or not. And so the value, and I'm doing this on a put option, so put option really pays off this determined K price, and that again, that's determined by the contract, minus S. So if K, let's say my stock price started at $50 and K is $50, if at time T, the stock price actually drops below K, below 50, I get a payoff. It's positive. If it's above 50, I get nothing. That's the max 0. That's what a put option is. And so I can actually come up with an analytical expression for what that is. I use the Black-Scholes formula in here. And so I can come up with my analytical formula for this. Right? So I call it analytical, it's pseudo-analytical. I have to do a numerical integration. But it's very straightforward. And the other thing I can do is I can calculate what that optimal threshold is for my price for exercising at tau. At capital T, it's clear. If S is, when S is equal to K, that's the threshold. Below that value, I exercise. Above that value, I don't. But somewhere in between, at tau, say halfway through, where I have my Bermudan option, I can calculate my theta star. Right? I'm not sure where that's going to be, but the math will tell me. Now, I can do the same thing in the simulation. I can simulate n paths, and I can calculate my valuation. And so what I'm saying here is my payoff is going to be K minus S at tau if I exercise. And then I discount that back to time 0. Or I'm going to get a valuation of K minus S discounted to time 0 again at t if I exercise at t, or I get nothing. So I don't have to put the rest are 0. And so then what I can do is I can keep running my simulations. I fix my 100,000 paths, and I just keep running this thing until I optimize on theta star, and the theta to maximize my value. And once I've done that, I can compare that to the numerical, the analytical solution, and if the two match, then the theory's matching the practical. Okay, so that's the simulation part for Bermudan put. Then I do the same thing for an American put. American put is no longer discrete, it's continuous. So I would expect an exercise boundary that goes across. I can't do an analytical expression for American put, but I can do it numerically through binomial trees and get something very close. But the idea is the same. I'm going to optimize my value by figuring out what my boundary looks like, my exercise boundary. Okay? So I can figure out my optimal parameters for that boundary by maximizing on my valuation. And then I can do the same thing for the build-abandon. And in the build-abandon, I have a number of states. I'm either not constructed, I'm either under construction, I'm operational, or I'm abandoned. Right? And I can run the same sort of simulations through. And again, I'm going to optimize on my value. And by doing so, I can again find my exercise boundaries. And that's the same thing here. Okay, so getting into the results, here are my parameters. So my initial stock price is 5. My strike price is 5. Tau is 1. So at time equals 1 year, I can either exercise or not. And at t equals 2, I will definitely exercise. If I haven't exercised here, I will exercise here if S is below K. I have a risk-free rate of 3% and a volatility of 10%. So the analytical result gives me 0.1688 and a theta star of 0.4757, right? What that means is at time equals 1, if S is below this value, I will exercise early. If it's above, I'm going to wait because maybe I'll get a better payoff. And so here are just some different simulation examples. So the purple line is the theoretical value. And the histogram is just all the different experiments I ran. So what I did is I ran this experiment, I believe it was 20 times or 100 times. I can't remember now. But I ran this experiment about 50 times. Let's call it 50 times. So when I ran it with 100 paths only, so I run it with 100 paths, I solve my problem. Then I run it again with 100 paths to solve my problem. 100 paths solve my problem. I wanted to see how big my standard deviation would be in my example. So you can see the standard deviation is pretty big, but my mean is pretty much on, both for theta star and for the valuation. When I run it with 1,000 paths, you can see that my standard deviation is really getting tight. 100,000, 1,000, 10,000, 100,000, million. And you can see that it is converging to where the theoretical answer is. So that gives me a lot of confidence that the methodology should work. In fact, there's a proof for this particular one that it will converge to the analytical. So here, if I look at number of paths versus standard deviation of value, you can see it decreases, and the same thing with my theta star, standard deviation of theta star, which is that optimum threshold of 4.75. Okay. Then what I did is I ran an American put. So this is a boundary. And I'm not going to get into the details here, but This is number of paths, and this is number of steps. I have to take so many steps in my simulation. And so I ran it with 100, 500, 1,000 steps, and I ran 1,000, 10,000, 100,000, 500,000 steps. And ultimately, I converged to the numerical result. Now, the question is, how do I build my boundary, right? Because this is an exercise boundary that is continuous now, because it's an American option. So I tried splines, and interestingly enough, you get some funny-looking boundaries, but the valuations are pretty close to what the theoretical is, right? Splines actually didn't work as well as polynomials. So use a second degree, third degree, fourth degree polynomial, and this is the optimal exercise boundary as determined using numerical methods. So you can see that this is the optimal, and using the second or third degree, it fits nicely, and the values are very tight. Then I use linear interpolation. There's some simple linear points, so I have a point here, and so on, and I can have 6 points, 5 points, 4 or 3 points. And again, here's the optimal value, and again, my valuations are pretty close. Right? In fact, this linear interpolation model is probably the one that I would use in the real options scenarios. Okay, so then the build abandon. Again, it's some parameters that I used here, but I don't have a numerical experiment for this because it's just very, very hard to do numerically. But here I have my valuation as I increase my path, so standard deviation of the value decreases significantly. And this is what the boundaries look like when you do 100 paths. I just picked a few. So kind of all over the place, but ultimately when you run it with 100,000, or is that 100,000 paths, you can see you get something that you expect. Okay. And this first part here, it can't give you an answer because you're starting here. So there's no probability of it ever going there, so you're just not going to know what that value is. It's just going to, the algorithm can't decide on that. So the goal is to apply this procedure in the real world setting. We utilize want to utilize 1 or 2 factor models for commodity pricing. Commodities are generally modeled better in 2 factor models rather than a single factor. So you're going to have 2 uncertainties. And then we can utilize managerial supplied estimates on managerial deposit amounts. And this is where we can utilize the learn as you go. And then we can have real options where we build, expand, mothball, and abandon. And Maria talked a little bit about this, and I spent a lot of time talking about the motivation for this. I'm not going to get into this right now, but the whole idea is we can have another stochastic factor, which is we can decide what this line looks like based on what managers tell us are their low, medium, and high probability values for how much ore they think might be in that site. And clearly, as you mine more ore, you're going to know better. And so you can utilize this process to help you with this. And it is a observable variable, because as you take out more, you learn more, right? So it is an observable variable, so it's nice to do. And so Maria walked us through this, and with the learn as you go, what happens is we can decide whether we should build 2 plants right off the bat, or a single plant, or whatever, depending on where we are in different states. So this really does address the issue of that mining paper, the one that looked at the 51 mines, and how the majority of the mines were built too big, too small, or whatever. Using these kinds of techniques actually allows you to use real data and managerial estimates to make some better decisions. But this is complicated. It's starting to get a little bit complicated. So what we wanted to do is actually make it so that we can run it in a machine learning environment. So in a very simple case, what we did is, again, coming back to the Bermudan put option, we created a neural net where our inputs were T over capital T. Again, capital T is a termination of the option. We looked at, we had another input of ln S of T over S naught, and the state 0 or 1, whether it was exercised or not. And then we had the value if it was exercised and the value if it was not exercised. This value is actually 0 all the time, so this node is actually not a value to us necessarily. And through a reinforcement learning environment, we ran this, and the way that reinforcement learning environment works is we take a single path and we let it run, and it keeps learning and learning and learning. Sorry, we take one path and the system learns on that path. Then we add a second path and the system learns on that path. Then we add a third path and the system learns on that path. And we keep doing that. And here are the different experiments we ran. So for example, this is from 0 to 100 paths. And then this is just exploded from 0 to 1,000. So this part here is pretty much this up to 100, okay? But what you're seeing is at first, the first number of paths, the machine is just not learning much at all. Right? Any one of these starting points, the machine is just not learning much. But as we go and we run more and more paths, the machine actually starts to learn. If we run this out to, this is 1,000. If you run it out to 10,000, you'll actually see that it actually converges very nicely. So we now have a machine learning algorithm through reinforcement learning that learns on its own when to exercise. I would argue that it's not practical computationally wise yet, but it really allows us for dealing with this complex problem of, what does this boundary need to look like, and what are all the different states that we can get into, and so on. So we're pretty excited by this work here. So in conclusion, the exercise boundary fitting methodology is consistent with financial theory. There's convergence and no bias. The exercise boundary fitting will allow for significantly more complex real option valuations that managers will understand. I would argue that simulations based using Monte Carlo, typically engineers get that. You show them a picture of a bunch of potential paths and they get what it means. We're looking at when to build, how big to build, when to mothball, when to abandon, and again, this idea of optimal rate of extraction I think is interesting as well, tied into the market price. That's